So let's go back to the osmometer lab, which was the one from last time. And let's just double check that everybody's on the same page here. Independent variable, dependent variable. Not deep. What was the independent variable in our lab?
Concentration gradient.
Yeah, it's the concentration gradient across the membrane. And the dependent variable?
Rate of osmosis.
Yeah, the rate of osmosis. We'll come back to this when we talk a little more about the discussion, because we're not actually measuring rate of osmosis. What are we actually measuring as our way to try to assess the rate of osmosis?
Time, like the amount of time it takes?
What's that?
Is it the time? Like the amount of time it takes, like whether it's faster or slower moving, or is it the distance?
Yeah, we're looking at the rate that the water is going up the tube, right? We're saying that is got to be related to the rate of osmosis, because the more osmosis is happening, the more water comes in, the faster the water is going up the tube. But that is we're going to see that can be tricky sometimes. The thing you're really interested is not what you're directly measuring. So then you have to make sure you understand how tightly coupled are your actual variable of interest and what you're actually measuring. And we'll see in this lab, to some degree they're coupled, but to some degree they're not totally. So what would be an objective for this lab?
How does the rate of osmosis depend on the concentration gradient across the membrane?
Exactly. That's all it is. Remember, these objectives should be really straightforward. Just how does the independent variable affect the dependent variable? Zip it, you're done. As long as stay focused on the independent and dependent. Hypothesis. For this, our hypothesis, we know that in our actual setup, we're looking at 40% versus 20% sucrose, in the osmometer. Osmometer. So what is our prediction given our actual setup going to be? And why?
Okay, so I revised mine. I put the higher sucrose solution, the faster the rate of osmosis will occur in the distilled water, because the 40% sucrose solution will move from the higher concentration to the lower concentration.
So that's kind of getting the solution isn't really, remember, the membrane doesn't let sucrose move. So it has to be about osmosis. It's about water crossing a membrane. So you're starting out. So she's saying that the higher concentration in the osmometer is going to result in a higher rate of osmosis compared to the lower concentration in the osmometer. And then why is that going to be?
Isn't it?
What's that?
Isn't it because the water is more attracted to more concentration, to a higher concentration, that it will move faster into the space?
Right, and it's going to be important though in your hypothesis that we're talking about concentration gradient. This is what's ultimately driving things.
Right.
And so concentration gradient only makes sense as a comparing two different sides. So when you're thinking about this, you want to think about not just what's inside the osmometer, but also what's outside. It matters that it's distilled water outside. So the gradient is the difference between the inside and the outside. So if I have the difference between 0 and 40 is a lot greater than the difference between 0 and 20. So that's important that you explicitly address that when you have the 40% in the osmometer, it's going to have a higher gradient compared to the distilled water outside. I make this distinction because if I put my osmometer with 40% inside, but then I also had 40% outside, what would the water do? Nothing. It
Wouldn't
would
move.
move. I can have 40% on the osmometer and have 0 osmosis if there's no gradient, if there's no difference between the two sides of the membrane. So it's important when you're kind of laying out your hypothesis that you make it clear that what's really important is the difference in concentration on the two sides. It's not just about what's inside the osmometer, it's also about what's outside the osmometer. So does that make sense?
So is it fair to say the 40% is going to have a higher gradient than the distilled water outside? So the rate of osmosis will be faster than the 20%?
Right. So I wouldn't say that. I'd say a higher gradient. That the gradient is the difference between 0 and 40. So it's because of the distilled water outside, the difference between 0 and 40 is greater than the difference between 0 and 20. So this condition has a higher gradient than the 20% condition. Right?
Okay, great.
Right. So the gradient is a difference. So you have to think about inside minus outside. Outside in this case is 0, inside can be 40 or 20. So 40 minus 0 is greater than 20 minus 0. So that's kind of what I want. I want people to really think about that gradient, the difference between the inside and the outside. That difference across the membrane is what's driving osmosis. So does that make sense? So if I set this thing up, I have some kind of stuff in here, and I put it in my distilled water. And let's say I start seeing the fluid run up. How do I know that sugar can't cross the membrane if I see this happening like this? Do I know for sure that sugar can't cross the membrane?
Well, there's a higher concentration of sugar, of solute. So if it could, wouldn't it move in the other direction because it's going to go down its concentration gradient?
Yeah, if sugar could cross the membrane, it would just go into the water, right? If it's 40% glucose or sucrose inside here, and it's 0 out here, if it could, it would just want to move out from high to low, right? So the fact that water is moving in means that this concentration is staying high and we have osmosis. If, let's say the membrane did let sucrose cross the membrane, what would I see after a little while?
The level of the water in the beaker go up.
No,
No?
no. How would that? The water wouldn't come from any place, really. If I
It would even out. It wouldn't move.
it wouldn't move, right? Basically, the sugar would equalize inside and outside the osmometer. There'd be no osmotic gradient. There'd be no osmotic pressure pushing the water up the tube. The fact that water is going up the tube means that we have osmosis happening, means that we have a concentration gradient that is being maintained. Does that make sense? So will water just keep go? Let's say and we have our osmometer. Will it just keep going up forever?
No.
No,
Why is that?
because eventually equilibrium is reached, and so it would stop
Equilibrium with what? What kind of equilibrium?
between the concentrations.
So that, if you think about it, there's always going to be sugar inside here. It's always zero osmolarity out here. It's never going to be balanced, right? It's always going to be sugarier inside the osmometer than outside. You could have, it's going to get more dilute as it goes in, but it's never going to be equal, right? It's always going to be zero outside, and it's always going to be some sugar water inside. If the sugar
Will it stop, or will it just like slow down so much that you like can't even really tell?
So one thing, we can have a slowing down because the concentration gradient is getting less. What other things are at play here that might be affecting the water going up the tube?
Pressure from the fluid in the tube itself, pressing back down on the pure water.
Yeah, what we call hydrostatic pressure. This is just due to gravity. Right, the higher the water goes up the tube, it has weight, and gravity is pulling it back down. So we call that hydrostatic pressure. It's the water pressure due to the height of the water. So the higher this column goes, the stronger that hydrostatic head, we call hydrostatic head is what they call the pressure. The more of that water pressure due to gravity that's going to be pushing the water back down. Does that make sense? So at some point, that's another thing that's going to be fighting osmosis. Osmosis is working to get the water from the beaker into the osmometer system. But then the more water goes up the tube, the more gravity is pushing down and stopping it and fighting back. So that's probably more where you're going to actually, when I forget who was mentioning equilibrium. There you actually are going to find some equilibrium. At some point, the water pressure due to gravity is going to balance out the osmotic pressure due to osmosis pushing up. And they're going to find some, assuming that you don't, that the tube is high enough. Otherwise, it's just going to kind of spooge out the top. So, but does that make sense? If this thing was sideways rather than going up, we wouldn't have that same thing. Then it could actually go on forever, slower and slower and slower, because the concentration is getting diluted inside. So there's less of a gradient, but you're not having the gravity fighting you.
So for question number 6, when you ask if this would go on forever, even though it could go on forever, the answer is no because of hydrostatic pressure.
Exactly. Exactly. The gravity is eventually going to fight and equalize against the osmotic pressure. And when we say osmotic pressure, it's basically how hard, it's like how hard do you have to push back to just equalize how hard the osmosis is pushing. So when the osmotic pressure equals the hydrostatic pressure pushing down, then the column of water will be in equilibrium, will no longer be rising or falling. Osmosis will be pushing up just as hard as gravity is pulling down.
PM.
Does that make sense? Yeah, because I wanted to go, I realized we need to kind of talk about this more explicitly so it makes more sense. So if we're like actually getting a little more explicit about hypotheses, like look at time and look at kind of rate of osmosis. What kind of relationship are we going to expect in this experiment? At some time equals 0, there's going to be, right, this is right when we start.
The rate will, like the rate increases, but like goes slower over time. So a negative, right?
So it's going to start at some rate, whatever it is, based on the difference between 0 and 40. And at each moment beyond that, everything's conspiring to slow it down, right? You're diluting the inside, which means less of a gradient. You've got more of a height, so there's more gravity pushing back. So you're going to expect something going down. It's never going to be faster than it was the moment it started, because the moment the water starts coming in, you're diluting the inside of the bag and you've got more gravity pushing down. So theoretically, you're going to expect something like this. Is that? What did we actually see in the data? I know some people have looked at this already.
I mean, it wasn't quite that, at least in the, wasn't quite dramatic of a drop down. There was a little more wiggle room.
What do you mean by that?
Like in the graph that we were looking at, like compared to what you just drew, the rate did go down. The rate did go down.
And
But
yeah, so I'm going to actually bring a couple of these things up here. I'm going to go share. So here's the osmometer, here's the data. And I can say this is a notoriously difficult lab to carry out well, because you have to seal things in water. As the pressure builds up inside that thing, it's very easy to have water leak out of things. If we look at the height graph, this is just the height up the tube as time goes by. Does this make sense? This is height up the tube. Purple is the sucrose 40%, blue is the 20%. Does this make sense?
Yep.
Yeah, it's saying like at 10 minutes, the 20% was 5 mils up, but the other one was, twice as high up. At almost each point, you can see the 40% one is twice as tall as the 20%, which makes sense. If you have water coming in faster, it's going to be going up higher in the same amount of time. Right? That should make sense. And then for the rate, we just took how far did it go up in the last 10 minutes and subtract, and divide by the 10-minute interval. So it went from 0 to 6 in the first 10 minutes. So the rate in that first 10 minutes was 6 mils per minute. It went from 6 to 12 in the next 10 minutes. So the difference between those is another 0.6, another 6 mils in 10 minutes, that's 0.6 again. Then it was going a little faster, then a little less. Let's take a look. This is the rate. If we look at the 40%, it looks pretty similar to what we said it should be. It starts high and just gets slower and slower. This one looks a little weirder though. This one doesn't look like it's getting slower, and then it seems to speed up and then it starts getting slower. I mean, what might be happening there?
the seal might be not as tight.
It could be the seal, or it could be the membrane isn't pulled as tight. So when the water first comes in, it actually is just kind of tightening things up, filling things up. And then all of a sudden it looks like it's going up because now there's no more room to just kind of pooch out, but instead it's going up the tube. And then we start seeing the real like, real, quote unquote, real thing where it should be slowing down the whole way, but we're not actually measuring osmotic rate. We're measuring height up a tube. So, my gut sense of what was happening is you have the system here, the water starts coming in, but it's not actually going up the tube as fast because it's actually just kind of tightening up, pooching out this little thing, tightening it up. So water's coming in, but we're not seeing it reflected in a height difference, right? So, we're pretending that the height change is the osmotic rate, but really it's connected. So if, at some point when this thing really gets taut, now any water that comes in is really going up the tube. But so my sense is the reason why it looks like it's speeding up in that case is just you have water coming in, it's just pooching things out, tightening up the membrane, but not going up the tube. So it looks like it's not going up very fast. But then once it gets tight, then all of a sudden we see it start going up the tube. It looks like it's speeding up, and then we start seeing the real thing where it's starting to slow down, because in reality, it's been slowing down all along. But it's just the initial influx of water did not go up the tube. Instead, it kind of tightened things up and swelled things out. That's my guess of why the data looks like it does.
I have a question.
Sure.
With the other, can you go back to that other graph that showed that it stayed constant, the rate graph? So we were talking about the 20% solution, and it's weird that it's constant and then it goes up, and you explained that. It's also strange that it kind of coincides with like not an increase, but it's with the 40%, it's decreasing rather quickly and linearly, and then it stops decreasing as quickly about the same time at 30 minutes as you see that other thing you wouldn't expect initially.
Right. I think, so all of these data points are kind of loosey-goosey, but I would say that this, I expect it to kind of start, this is starting to become more asymptotic, which is kind of what you'd expect. It's kind of starting kind of fast, but then becoming kind of less and less. I don't know. I don't know though. I would say I would not put too much, get too fancy in the theorizing, given how kind of messy the data is, or ascribe much meaning to like anomalies that you see.
Okay.
That's what I would say. I would say if we did this in a much more rigorous way and did it with more, more data, and we started seeing interesting, weird things, then we might think, oh, what might that really mean? But given that there's only a few groups and it's a notoriously tricky lab to get right, I would not put too much energy into interpreting what's probably kind of noise. Yeah, so, but when you're looking at this, you can definitely see for sure that higher concentration gradient resulted in more water coming in faster, which we can see going up the tube. We saw overall for sure the rates for the 40% were greater than the rates in the 20%. The exact relationship over time is a little weird. And in your discussion, you should say that this is weird, that the 20% is not doing what you expect. Like that's part of what a discussion is saying like, I expected it to just slow down for the whole time, but my data here says it actually sped up at some point. Like, what's up with that? Right, so that should be in your discussion, should ask like, why is it speeding up when it should not be speeding up? The other thing I'll mention, I have noticed that maybe I didn't, when you're using figures in your discussion, any figures, tables, etc., need to be numbered. And refer to number in discussion. You can't just have like orphan graphs and assume that I'm going to put it together and figure out why you put it there or how it fits into your discussion. You need to make sure that, in your discussion, you have that, rate versus time, and there's like do, and there's the, boom. And then you call it like figure 1, and then in your discussion, as we see in figure 1, the 20, as we see in figure 1, the 20% seem to speed up at 30 minutes, which doesn't make sense and probably has to do with some problem with our setup or something. But you need to make sure that you integrate your graphs into the text using figure numbers. So just kind of putting that out there. What else about this osmotic lab? Any other comments or questions about what people noticed doing, looking at this? Hopefully I know some people have already looked at it in quite a bit of depth. Then there was the auger diffusion. Was there anything surprising about what happened when potassium permanganate and methylene blue were diffusing in the auger? And what is the difference between potassium permanganate and methylene blue?
The size
Their
of
weight.
that solute.
Yeah, the weight, the molecular weight. We talked about how potassium permanganate is only half the molecular weight of methylene blue. And if you take a look, the thing that weighs twice as much is diffusing about twice as slow. So we get actually really nice data there. Right, so that is just kind of a nice little support for what we talked about, that rate of diffusion is going to be inversely proportional to the molecular weight of the solute there. Why did we do it in auger rather than just put it in water or something to measure this? Why did we use the auger?
Because it's easier to see.
Because it's stable and has no current.
Exactly. It does not have any currents. We talked about the idea of diffusion versus convection. Convection, the flowing of the air or the water that transports things much faster than diffusion would. You can see that data I just showed you, that methylene blue was sitting there for an hour and a half and it didn't even go a centimeter. It did not go very far. Diffusion does not take you very far, very fast if you're looking at distances that are more macroscopic. Most of the time when we're thinking about diffusion in the body, we're thinking about diffusion over fractions of a millimeter. We're going to talk about, here's a blood cell and here's the tissue cell, and oxygen is diffusing a fraction of a millimeter, like microns. We're going to be talking about diffusion happening over very short distances. Or when we talk about neurotransmitters going from one neuron to another, they're literally having to diffuse like 40 nanometers, 40 billionths of a meter to get from one neuron to the next. So that happens pretty fast. If you're diffusing over a few billionths of a meter, that you don't have to worry about how long does it take to diffuse. But diffusion is not very efficient if you're working at larger distances. Again, like I mentioned, that's why you have blood flow. You have diffusion gets the oxygen in your lungs into the blood, and then you flow it all over the place to get close to your cells. And then you can use diffusion for that last fraction of a millimeter from the red blood cell to the tissue. Same thing, even getting the oxygen into your lungs. You have to do the bulk flow of oxygen. We'll talk about all the pressure differences to bring the whole air down into the lungs with a big flow. And then once the oxygen is down in your lung tissue, you can do the last little bit of getting the oxygen into your bloodstream across the wall of the alveoli using diffusion. But diffusion only works efficiently over very short distances. And so that's what we wanted to show in that experiment. Hopefully you watch the video where Tina puts the dye into the auger, and you can actually see it kind of diffusing slowly away. Auger is basically kind of like a matrix that kind of holds, it's like Jello. It holds the water in place, so the water can't actually have any currents. So then you're seeing pure diffusion. If we just put it in a tub of water, there would just be all sorts of flows, and we wouldn't even be able to, you would just see things drifting around due to the water currents rather than pure diffusion. Part of the reason I still like to do that thing with the methylene blue and potassium permanganate is just to really drive home how frickin' slow diffusion is over larger distances, right? In fact, maybe I should go back. Let me share.
So you have a half hour here, but you're gonna.
So 60 minutes. This is an hour.
All right, so we're here at our diffusion experiment, and we're gonna do our time after 1 hour time point. The edge of the well, and in this case, it looks like 7 millimeters for the potassium permanganate.
But you can see it has not gone very far in an hour, right? And actually, if you just leave this here in the lab overnight, it's not even going to make it to the end of the Petri dish because it gets slower and slower as the concentration kind of gradient gets less as it diffuses further out. So just kind of really driving home, diffusion is going to be fine if you're crossing a synapse or going from a red blood cell to the surrounding cells right nearby it in the tissue. But diffusion is pretty slow in this more macroscopic thing of trying to move millimeters or centimeters or something. So it's one of the take-home messages I want people to kind of get more of the intuition of what is diffusion, what is it, where is it useful, where is it not useful. Again, why do we have, we'll talk about this in more detail when we get to the cardiovascular system. But the only way we can become a larger creature than an amoeba, amoebas can use diffusion to allow oxygen to get to every part of their body. If you're like, Andy amoeba, you can just let oxygen kind of diffuse in. You're happy, but you're also microscopic. If you want to be a big animal like us, what you do is you make yourself out of trillions of individual little cells, trillions and trillions and trillions. This is ultimately going to be you, but you're made out of trillions of little cells, and then literally 100,000 kilometers of blood vessels traveling everywhere and bringing the supply of oxygen stored on the red blood cells within a fraction of a millimeter of every one of these trillions of cells to make sure they get their oxygen, because that diffusion only works on that small scale. So you got to use the bloodstream to bring the blood up close to every single little cell. And that's how you can become a large creature. Even though oxygen is not going to diffuse very far, you need to make lots of little cells that you then use this plumbing to bring the oxygen up close. So diffusion can take it the final bit. Blah, 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 blah. So any questions about osmometer and diffusion labs from last class? I wanted to make sure we actually slowed down to look at the main messages from those labs, so you didn't feel like we're just kind of blasting through it. The lab that we were going to do today, and that I still, hopefully you've done the pre-lab, is taking a lot of these concepts and extending them more to the real world of our cells, and then actually doing it with real cells so you can see what happens. The fluid balance and RBC lab. I am going to talk about tube 1 because I saw hilarious stuff that. So what is the solution in tube 1?
Distilled water.
It's distilled water. So people get confused here. Distilled water, there is no solute. So people start talking about penetrating, non-penetrating is not applicable in tube 1 because there's no solute to penetrate or not penetrate. We're assuming water can penetrate because otherwise we wouldn't have osmosis. That's every case water is moving across the cell membrane because that's what osmosis is. But there's no solute, so it doesn't make any sense to say penetrating or not penetrating. What is the osmolarity of this? How many moles of particles are there per liter of distilled water with no solute?
0.
Zero osmolarity. So there's 0 osmolarity, which obviously is less than 0.3. So in terms of would I say hypo, iso, or hyperosmotic?
Hypo.
It's way hypoosmotic. And what about tonicity?
Hypo.
It's going to be way hypotonic. Hypotonic with a vengeance. If you're a plant cell, you can deal with it because you've got a cell wall that pushes back and holds its cellulose. It's the turgor of a plant, how plants like stay stiff and grow up tall. But if you are an animal cell, you are in trouble. What happens to a animal red blood cell if you put it in distilled water?
Lysis.
You get what we call hemolysis. You know, the hemoglobin just is going to go into solution. The cell membranes are just shattered. What is this going to look like under the microscope when you try to see these guys?
Just red.
So, you know, there's going to be red just in the liquid, in the solution. What are you going to see the cells at all?
No.
No, so they're people. I mean, when we do this in person, people get frustrated because they're trying to see what they can see. And if I don't, you know, imagine you're in a room full of balloons right before New Year's Eve, and the room is just filled with balloons everywhere. And then the, you know, clock hits midnight and pop, pop, everybody pops every single balloon. And then you look around and the room is empty. You know, maybe you look on the ground. Oh yeah, there's like little bits of rubber lying around, but it's kind of like that, right? These things are exploded. You're not going to see a whole lot of interesting stuff when you look at this under the microscope. What if I take something that is slightly hypotonic? You know, so I'm 0.3 in the cell. What if I was just like 0.3 osmolar? I mean, what, this is outside. So now the gradient, right? The osmotic gradient, which is what's important, is less. The difference between 0 and 0.3 is very strong. So water comes in with a lot of osmotic pressure. If I have a much lower gradient, maybe it's only 0.1 across. What might I find?
Crenation.
Swollen cells.
Yeah, so yeah, not crenation. It's still, water's still going to go in, right? It goes from to where it's more concentrated, but it's not coming in with as much osmotic pressure. Similar to what we saw with the osmometer, with the 20% across versus the 40% across the membrane. It comes in, but it doesn't come in as fast or with as much force. So it might just swell, and maybe we're going to inflate the cell, but not actually explode it. Right? So you can have hypotonic, but not explode the cell, not have hemolysis. It could be that it just swells if it's slightly hypotonic.
Is that because the gradient is very small? It is a
Exactly.
very small gradient. Okay.
Yeah. A small gradient means there's much less osmotic pressure.
Will it eventually, if you just let it stay there forever, will it eventually burst or not necessarily?
No, because it's think about a balloon. If a balloon has a certain amount of ability to push back against the pressure and just stay as a balloon, but if you blow in too much pressure, it'll pop on you. So there is a limited amount of pressure that this thing can adjust to and hold its own. But if you overdo it, it's going to explode. So it's more like that. What if I had like 0.6 osmolar outside instead? What would happen?
That's where it would
Crenation.
Yeah.
That's where I'd see the crenation. The water would now leave this and go into the solution, and my cell would all get shriveled up. So
Where do you draw the line on crenation versus what you were talking about earlier with the smaller gradients? Like, where do you draw that line? As
I'm not
far
sure
as
what you mean.
with the 0.6, with a 0.6 osmolar versus 0.3, and the higher gradient versus the smaller gradient, where is that line drawn that it would be crenated versus what we were talking about before? I can't remember what we were talking about.
Wouldn't it be anything over 0.3?
Anything over 0.3, you're going to start losing water and crenating, right? Anything below 0.3, you're going to be taking on water and starting to inflate. And how much you inflate depends on the osmotic gradient. If you really overinflate, you're going to pop and hemolyze.
Oh, gotcha. Okay.
Right. So as long as this outer solution is anything greater than 0.3 osmolar, water is going to leave. You know, how much and how fast, it's going to depend on the gradient, but water will leave, the cell will start shriveling up. So this is kind of like that magic number. If you're at 0.3, we're in equilibrium and the cell stays happy. If we're above 0.3 in the solution, we start crenating. If we're below 0.3, it will start inflating a bit. And again, slightly hypotonic isn't necessarily a disaster. It just means things take on a little more water. But very hypotonic is a disaster.
Can you have slight hypertonic?
Yeah, of course.
So it doesn't totally crenate? Just
Yeah.
Would that depend on if it's penetrating or non-penetrating?
The penetrating, we talked about, if it's penetrating, typically what happens is the solute goes into the cell and then water follows the solute and you end up in a hypotonic condition. In general, a penetrating solute is going to go in, and as solute increases in the cell, water is going to follow, because that's what osmosis is. As the solute goes up in there, water comes in to kind of, you know, dilute it, so to speak. Right. So things that have penetrating solutes tend to be hypotonic like that. So it's 12:30. What I would do is, if you have not got a, you know, approved pre-lab for this, make sure for each, you know, for each of the 9 tubes, you know, you have your prediction and the Y. You know, so you want to tell me what you expect to find to happen to the blood cells in that tube and why that makes sense. And you can support it using kind of the analysis from like that spreadsheet that you all have. So hopefully does this make it a little clearer? Yeah, and again, the more we do this, the more it's going to just get more intuitive. And like I said, osmosis is going to be, you know, at the core of the whole urinary system, like, you know, 3 months from now. So it just, the more you get intuition about this, the better. As you know, because then it's just, oh yeah, I see how that's all going, rather than wait, how did it go? So, all right, so I am going to be here for the next hour, but we are officially done in terms of our class.